This is the last lecture of this term. The last week, the last lecture of this term and this course. And today we will talk about MPLS, and also we have some topics about data center networking. Okay, we will start with MPLS first. According to the history, in the internet, we are using IP. IP networks are scalable. What does it mean? It means that, for example, currently I have a class. Okay, I'm joining to the class via internet. So firstly, I connect to internet. I'm finishing my class, and after that, I will disconnect from the internet after the class. Okay, so simply I connect to internet, became a member of internet, and finally at the end of the class I will departure the internet. But the current structure of internet accept this modification, adding a new person and dropping him. Okay, so this structure, the structure of current internet, is scalable. But we know that this structure, the structure of current internet, is slow. So we are looking for something else about the speed. On the other hand, we talked about virtual connection, virtual networks, virtual circuit networks. In chapter 1, we talked about virtual circuit networks. We said that virtual circuit networks is something between IP and circuit switching technology. For example, ATM, frame relay, X25. They are something between IP and circuit switching. Datagram and circuit switching. Okay. For example, when I'm talking about ATM, asynchronous transfer mode, in ATM, we are using small fixed size packets. We call them cell. The ATM has cell. Instead of packet, we call them cell. Each cell has 53 bytes length. Okay. The ATM switching capability is very fast. It's too fast. That's great. The switching speed of ATM is too fast. But because of its base, the base of circuit switching is, the base of virtual circuit switching is circuit switching. The circuit switching technology is not scalable. So the ATM has limited capacity for scalability. So we have two different areas, two different types of network. One of them is IP, which is scalable with low speed switching, and the other is ATM with high switching speed and low scalability. Can we mix them and create a new type of network? Cisco answered this question. Cisco and some other companies, such as IP Ceylon and somewhere else, answered to this question. Cisco proposed packet switching mechanism, and finally IETF proposed a new protocol. We called it multi-protocol label switching, or MPLS. Multi-protocol label switching. Multi-protocol. multiple protocol. Okay, so we are talking about multiple protocol. Those protocols are using label switching. The goal, what is the goal? The goal of MPLS. The goal of MPLS is that I'm using IP network, IP structure, okay, on layer 3, and a switching mechanism, a new switching mechanism, such as similar to virtual circuits networks in layer 2. So MPLS has great scalability, such as IP, and it has good switching speed because of its label switching or switching capacity on layer 2. So we are looking for something new. We are presenting, we are proposing in something new. What does it mean? What is the difference? Still, I don't know what is that. Okay? So we need to discuss about MPLS more deeply. You know, in IP, the speed is low. Why? Because when an IP packet arrives to a router, that IP router will process the header of the packet, and after that it will look up for the address. This address lookup is time consuming. This address lookup. But we're talking chapter 4 about the structure of IP addresses. And we said that, okay, in IP address, we have two different parts, net ID and host ID. We should define, we should clarify the subnet part in the address. And so we need a mask plus the subnet ID. We put them in the routing table or forwarding table. And then when a new packet arrives, we apply the mask on the destination address to find the best, to find some new destinations, some destination, and among those destinations we talked about longest prefix match to find the final destination, final forwarding path toward the destination. Okay, we talked about all of this, but this process is time consuming. So IP routers are slow, but in the ATM, for example, a new cell arrives. In that cell, we have one or two ID. For example, in ATM, we have VPI plus VCI, two different identifiers. Okay? We just to check VPI and then VCI. They are very small. For example, VPI is a 12-bit identifier and VCI is 16-bit identifier. They are very small comparing to IP address. IP address is the IP address version 4 is a 32-bit address, but VPI is 12-bit. 32-bit means 4 billion different addresses, but 12 bits means only 4,000 different VPI. Okay, so they are completely different. VPI and VCI also. VPI and VCI are local. It means that this VPI and VCI only present between this system, this switch, and the next switch. In the next switch, I will change them. I will change the VPI VCI. Okay. So the switching in the ATM is very fast, because just they need to look in small switch tables, just not in too large tables. So switching is very fast. In MPLS, we are moving to use a similar structure. Instead of focusing on IP address, we are focusing on a label, called it label switching, multi-protocol label switching. We are focusing on this label instead of focusing on IP addresses. Okay, so we have an IP network, layer 3, layer 4, layer 5. Okay, and in bottom we have a switching strategy. We can use different switching strategy here in this case in MPLS. For example, if I use ATM or frame relay or X25 as the switching platform here in layer 1 or 2, I can use their structure for instead of label. I don't need a label. For example, if I use ATM as a switching layer, the ATM has VPI and VCI, so I use them as the label. Okay? But for example, if I use Ethernet network as my platform, my physical platform is Ethernet, or triple P, it's another platform, Ethernet or triple P. In these platforms, we don't use something like some identifiers such as similar to ATM IDs, similar to family IDs or something like that. Okay. So what we can do here in this case, in Ethernet, in triple P. Why? Because as we talked, in current internets, the Ethernet technology, the Ethernet networking technology is dominant in current days. Okay? And Ethernet has not VPI, VCI, or something like that. So what should we do in this case? In this case, here, look at this one. This is a frame. This is an Ethernet frame. The Ethernet header is placed in layer 2, and we have some other payloads from layer 3, layer 4, and something like that. Here, right between the header of layer 2 and header of layer 3, between header of layer 2 and the payload, layer 3 and the other ones, okay? Between them, we call it layer 2.5. We call it layer 2.5, 2.5, okay? 2.5, layer 2.5 or 2.5. We will add a new header. We call it shim header. We will add a shim header. Shim header is a 32-bit header. It's a 32-bit header. It's a 4 byte headers. The first 20 bits of this header, the first 20 bits of shim header is a label. Wow. In Ethernet, we has not a label. So I'm adding a shim header, and inside this shim header, we have a label, a 20-bit label. Also, this shim header has some other fields such as experience, 3 bits for experience, 1 bit for stacking, and 5 more than 5 bit for TTL. Okay, but currently forget them. I don't want to talk about them. For example, stacking means that I can push one label into another one, sticking one label over another label. Okay, I can do this. For example, if I during the pass of the pass toward the destination, maybe I have to leave my MPLS domain, enters into another MPLS domain, and again enter into my MPLS domain. In this case, I have to use stacking. In the second MPLS domain, which is not mine, okay, another label is pushing onto my label, into my label. Okay, just forget them. Focus on the label. This label acts similar to VPI, VCI in ATM for me in internet. I'm in internet. I'm talking about internet. This label, this 20 bits label, this label acts similar to the to that labels in in ATM, in frame relay, in X25. So now I have a special router. My router can act similar to a common IP routers. Excuse me for the interrupt. So I have a special router. This router can act similar to a common IP router. Okay, but currently we have a shim header too. So my router can act using this shim header. How? For this shim header, we have another routing table. We called it label table or something like that. Okay. In this table, we put the information of those labels. So when a new packet arrives, instead of checking the IP addresses in layer 3, the router will check the label of the the label of the packet. Just the router will check the label of the packet. It's a straightforward. Just check it and okay, this packet with this label move toward this pass forward in this way. So the router never checks the IP address. And as I talked in this lecture, the address lookup is the problem in IP networks. This process, address lookup, this process is time consuming. And now I'm removing this process. Instead of looking for the IP address, just I check the label. Check the label and find the forwarding pass. Okay, forward the packets in this way. Okay. So we are using another option. We have another option. My router can decide what it can do. It can work based on the IP address, or it can make decision based on the label. That is great. So I can assign a label for each flow. If you remember, when I talked about IPv6, I said that okay, the scientist added a new field, flow label, to IPv6 to handle the flows based on their requirements. And now, in MPLS, simply I can assign a label to each flow. So the package belongs to each flow has a specific label. So the router will act similarly for each of those flows. Packets belongs to each of those flows. When I'm talking about this structure, maybe think about something else. You know, in current IP networks, when a new packet arrives, I should look in the forwarding table or in the routing table to find the path. As we talked, this table is changed over the time using the routing algorithms. For example, OSPF, IS, BGP, or something like that. Okay. So the routing table can change, but here I'm talking about a fixed label. This label does not change. So I can say, using MPLS, firstly I'm creating a path, a fixed path, to forward the packets between the source and destination. I'm creating this fixed path. I'm set up in this fixed path. And after that, after defining the labels and registering those labels in different routers, I will forward the packets with those labels. You know, those labels are locally. It means that I use, for example, label X between the router 1 and router 2. And in router 2, I have to change this label. I'm changing it to something else. Those labels are local. Okay? But firstly, I'm installing a path. I'm using a signaling protocol to install, to set up this path. And after that, you need something near or close to ATM or virtual circuit or circuit switching. In circuit switching, we said that in circuit switching, firstly we set up a path, and then we forward the packets over that path to our destination. Something similar happens in MPLS. One more interesting idea here. I'm creating a primary path for each flow. Some flows are important. I need to protect them. So, can I define a backup path for them, backup route for them? Yes, exactly. In MPLS, using the structure of MPLS, I can define a backup path, a protection path for some flows, some important flows, not all of the flows, the whole flows. That's for some flows which are important for me. I can define some protection passes. What does it mean? It means that if my primary pass fails, I don't know why it fails. Okay, simply I can reroute my packets into another pass, into another way, into the backup pass, through the protection pass. This pass is created in the past. When I set up the primary pass, I set up the backup pass too. So simply, if my primary pass fails, rapidly I can change the pass. Okay, move forward these packets into this backup route. Simply. But when I'm talking about IP networks, in IP networks, firstly, the routers should define those failures in the past, and then we have run the routing algorithm to find a new path, and then again forwarding packets into the new path. Okay, it takes time, but sometimes for some things, for some traffics, I have not enough time. For example, something like teleprotection in electrical industries. This application is very restricted. It's very time sensitive. Very time sensitive. I have no chance, or I have no time to calculate, to find a new pass or something like that. When the primary pass fails, right at that time, I should change my pass into another route. Okay, or I'm talking about something like a video conference. I have some restriction. I have some time sensitivities, something like that. Okay. Also, I'm talking about a primary pass or maybe a secondary pass. So, can I set up the pass based on traffic engineering capabilities or properties of the flow? Yes, exactly. I can set up a pass based on the quality of service requirement of the traffic. It means that, for example, I have a special traffic with some delay requirements. Okay, when I set up the pass for this traffic, I'm saying, okay, this route must support this delay requirements, this QoS requirements, quality of service requirements. That is great. I have a chance to create some new routes based on the quality of service requirements. So MPLS is a great platform. It can help the IP routers to forward packets very quickly. It can help me to set up backup routes. It can help me set up passes with traffic engineering capabilities. It can help me to set up passes with limited power consumption, with limited processing capabilities, something like that. That is great. It's something in MPLS we are talking about something near to features, not a router. A router has lots of software capabilities. But here we need just a few software capabilities. We are looking to forward packets as soon as possible. So MPLS capable routers are strong. Look at this one here. I have two different traffics, one in red, one in blue, and the other in green. Okay. If I use common IP routing technologies, common IP routing algorithms, you can see those flows, the blue and the green one, are forwarding through the R4 to R2 and R1. They are using similar passes. Why? Because of routing algorithm, common routing algorithm in IPs. But if I use MPLS, I can define those passes. Okay, for example, for the blue, we can say, okay, the blue flow should forward from R4 to R3 and then R1. You know, we made it clear. Okay, the route for the blue flow is R4, R3, and R1. And the green flow should be forwarded from R4, R2, and R1. I make it clear that those flows use different passes, different routes. You know, in MPLS, we can use common routing strategies in IP networks with some modifications. For example, we can use OSPF or ISIS routing algorithms. So in MPLS, I can use them, but I can use another techniques too. For example, source routing. It means that the source defines the passes toward the destination. Maybe strictly, maybe loosely, I don't know. Okay, it's not important, but the source can detect the passes. Okay, my packets should be forwarded through this pass. I like this one. It's not on your business to think about that. If you can support this pass, let me know. If you cannot, again, let me know. But this is my only choice. You have not enough right to change my choice. I like this pass. Just this pass, not the other passes. Okay? This is one of the main capabilities in this. So MPLS has lots of capabilities, especially when we are talking about routings, finding a path between the source and destination. Also, during the past 10 to 20 years ago, during these past 10 years, we can see some scientists are working on a generalized MPLS format, or GMPLS. It's a generalized form of MPLS. And MPLS, using this structure, MPLS can supports backup routes and as soon as it detects a failure in the pass, in the primary pass, it can reroute the packets very fast as soon as finding link failures in each of those passes. But one may ask me, okay, Mr. Afarian, how we can set up a pass between the source and destination? As I said, we can use common link state routing algorithms in IP. You know, we have two types of routing protocols in computer networks. One of them is link state, the other is distance vector. In distance vector, such as RIP, RIP, each node has a limited information about the area surrounding it. Okay, its information is limited. But in link state, firstly, the node must detect the whole structure of the network, the whole graph of the network, and then it decides about the routing, make a decision about the routing. Okay, so in MPLS, we are using link state algorithms such as OSPF or ISIS algorithms. There are some modification on them, and we can use those modified versions in MPLS routing. So in primary, we can use those simple routing structures in MPLS. But sometimes, as I said, I can create some special passes, some special routes based on something in my mind. Okay. Oh, I like this pass, this route. Okay, it's my choice. In this way, we can use something else. We have a protocol, we call it RSCP-TE. TE means traffic engineering. It's a version of RSCP. RSCP is a protocol which is used in int-serve architecture. Int-serve or ISA structure. It was the first. It was one of the proposed structure for internet to protect quality of service in internet, but because of its overhead, nobody accepts this structure. In ISA or int-serve, we are looking to support quality of service for each of the flows in the internet. But we have millions of flows in the internet, so routers cannot support this structure. But here in MPLS, I'm talking about just a few flows. So if you have a few number of flows, just a few, never think about too many flows, just for a few flows. Please remember this, just for a few flows. We can use RSCP-TE. It's a version of RSCP specialized for MPLS. Okay, I can use RSCP-TE signaling protocol in MPLS to set up a predefined pass. Okay, just I need this pass with these requirements. I can add my requirements, my quality of service requirements, my specifications about the pass inside the RSCP-TE. Okay, everybody, can you set up this pass? If you can, please set up it. If you cannot, let me know. So pay attention. Maybe it be success? Maybe. No, it lost. I don't know. But using this structure, I can define some primary passes, some primary and backup passes for some special. So just a few special applications. Again, I'm repeating, just for a few. You cannot use RSCP or RSCPT in your devices for too many flows. Even in Cisco devices, the Cisco guarantee that you can use RSCP for some few applications. Okay, but the Cisco, if you read the documents, the Cisco documents, they say that okay, if you decided to use RSCP, just use for them. Just use this technology for less than 10 applications because of its overhead. RSCP and RSCP-TE, they have a huge overhead. Okay, the overhead is heavy. So if you set up too many routes, you can see that okay, your network, the performance of your network would degrade. Your network will collapse because of this overhead. Your routers have not enough time to answer the requirements of other applications, other traffics. Okay. Look at this slide here. In this slide, you can see the structure of MPLS forwarding table, or we call it label forwarding table. Instead of the common routing table, we are using another table. We call it label forwarding or MPLS forwarding table. Here you can see we have different columns: input label, output label, destination, and output interface. You know, some of these information are repeated from the common forwarding table or from IP forwarding table, but here we have two special columns. One of them is input label, the other is output label. When you are entering into an IP MPLS domain, here, this one here, this is an IP MPLS domain. MPLS domain. Okay. When I'm entering into an MPLS domain, my packet has not a label. So here in R4, you can see that we have not input label, but the packets would receive an output label. For example, the packets comes from destination 6, comes from router R6 into R4 for destination A. This packet will receive a shim header with output label 10, and they should forward to interface output 0 to this one here. Okay. In R3, we receive packets with input label 10 for destination A. Those packets, the label of those packets should be changed into 6, and those packets should be forwarded over the interface number 1 here, this one here, and here. If we receive a packet with input label 6, that packet should be forwarded into the A. Without any label, it should forward through the interface, output interface 0. Why we remove the output label? Because this is the R1 is the end router in this domain. The domain is finished, so I don't need labels. So simply I remove it. In the table you cannot see the output label because the domain is finished, is ended. The R1 is a router at the edge of the domain. So simply I remove the label. I remove the shim header. So this is the forwarding strategy in MPLS. Simply I'm forwarding packets with those labels through different routers. And you can see that the labels are local. They are important only between two different routers. At the receiver, we change the label into a new one. And then we forward the packets. And now, here, you can see that instead of IP addresses, I'm focusing on labels. I'm handling the labels only. These routers here, these MPLS routers, they just think about the labels. They never think about the layer 3 contents. They never think about the IP address of the destination. Okay? They just switch the labels when the packets is forwarding through the pass. Just the routers check the labels, define the output interface, and forward the packets over that output interface. And they change just the labels, nothing more. Okay? So MPLS is a powerful structure, is a powerful architecture to increase the speed of internet, to support IP addresses, to support primary and secondary passes, protection passes, to support quality of service. It's an interesting structure over the internet, over the current internet. So nowadays, if you look on internet, you can see that in most of newly proposed network, the designers will design IP MPLS networks, not an IP network. They are focusing on MPLS networks. Okay. The last part of this course is talking about data center networks. In data center networks, we have tens, thousands, maybe hundreds, thousands of hosts of servers. They are closely connected, coupled with very high speed interfaces in a small area inside different too many racks. They are facing together in small areas. Okay. We are using data center for different reasons. For example, Akami is using it for e-business. Excuse me, Amazon, eBay. They have their data centers for e-business. For example, Microsoft, Apple, Akami, YouTube, and something like this. These companies are using data centers for as content provider places. Google is using data centers for its search engine, for data mining, for as a content provider uh, for some services such as Gmail or something like that. Okay, so different companies are using data centers for different reasons, but a data center is a big place with too many hosts, with higher speed switches and routers, with higher speed connections, with multiple applications serving different number of peoples, serving maybe 100,000, 10,000, 100,000, or maybe millions of peoples or users. These structures needs reliability, higher rate of reliability and availability, because they are supporting too many users, maybe million users in a short period of time. Okay, so they have to be reliable. They need a high reliable rate, very high reliable rate. In data centers, we need to manage the traffics inside the data centers, managing different traffics, different routes, loading the balances between different uh, um, servers, between different parts in a data center, avoiding extra processing, avoiding congestion in networks, in congestion inside the data center networks, avoiding bottlenecks in data centers. You know, we have very basic and challenging problems in data centers. We should be care about them. A data center has a wide bandwidth, so I should manage it very carefully. For example, when I'm talking about load balancing inside a data center network, this load balancing is very important. Why? Because it's very important because if the big portion of load is forwarded to a specific part of the data center, that part would be congested, and it couldn't answer to the queries in a short period of time. You can check it. For example, you can Google. You are typing something in your Google and then pressing enter. You will receive the answer to your query just in a portion of a second. For example, 10% of a second. Wow, that's great. But how? Because the Google has a strong load balancing technology. The Google uses a strong load balancing technologies. The Google server receives millions of queries per second. Millions of queries. So they must balance those queries between too many servers to answer them in a short time, just in a few percent of a second. Okay, this picture here is a is an image from the data from the Microsoft data center in Chicago. Okay, but so we need to handle this special congestion, and sometimes if you read the papers, you can see that, for example, those big companies, Google, Microsoft, Akamai, YouTube, or something like that, they are using special types of TCP inside their data center networks. Inside their data center networks, they are using some special types of TCPs. Even they are working on this part, on TCP performance in their data centers. Okay. If I look on the architecture of a data center network, I can see something like this here. In this structure, the first thing that I see is that this structure has a strong redundancy. What does it mean? For example, here, instead of using one router, we are using two routers. Instead of using just a few links, we are using too many links between the devices in one level and connected to devices in the another neighbor level. Okay, this is the border routers, and then the tier 1 switches, and then tier 2 switches. We have different switches and routers in different levels, and they are connected together. They are connected together with too many redundant links. Why? Because I said that one of the main challenges in data center is availability, is reliability. And the only answer to the reliability issues, to the availability issues, is using redundancy. This is the only answer. Okay, you can see here, there are several routers and switches in different levels. Each of them are connected to different switches and routers in the next layer. So we have too many redundant passes between different levels, between different connecting devices in different levels. Okay. So, for example, if I lost one of these switches in tier 1, it's not important. There are some other routes that they can handle my request. Okay. Just simply, I can reroute the queries over another pass to other destination. In the lowest level, I have some racks. In top of those racks, I have a switch. Okay, top of rack switches, and inside each of those racks, I have several switches, several servers, several blades of servers. Those servers are handling the queries, are responding to the users. And the connection, the speed of this connection here between the border routers, between these switches, the speed of these connections is 10 gigabit per second, 40 gigabit per second, 100 gigabit per second, something like that. So those links are high speed. Are using those speed. Those links are high speed with very high speed. We are using very high speed switches. We are using very high speed uh, links. Okay, look at this one here. This is part of Facebook data center. You can see here in the top part of this structure here, you can see different number of switches and a switch fabric, and finally those switch fabrics are connected to top of rack switches. This is a structure uh, handling the queries, are responding to the users. And the connection, the speed of this connection here between the border routers, between these switches, the speed of these connections is 10 gigabit per second, 40 gigabit per second, 100 gigabit per second, something like that. So those links are high speed. Are using those speed. Those links are high speed with very high speed. We are using very high speed switches. We are using very high speed links. Okay. Look at this one here. This is part of Facebook data center. You can see here in the top part of this structure here, you can see different number of switches and a switch fabric, and finally those switch fabrics are connected to top of rack switches. This is a structure F16, Facebook F16 data center. Okay. So we are creating multiple passes between each switches and each rack, each of those servers inside the racks. I have different connections. For example, here I want to connect to rack number 1 or rack number 11. If I decided to connect to rack number 1 using this switch here, I can follow these red lines toward the rack 1, and the other red lines is connects me to rack number 11. The blue passes here. This one connects me on this switch. I can follow this blue lines toward the rack number 1, and I can follow these blue lines toward the rack number 11. You know, I have different routes toward a specific racks. This is the redundancy. And I'm talking about redundancy to increase the availability rate, to increase the reliability rate. I prepare different routes between the top level switch and routers and low level racks. Okay, I have these different routes. So simply I can choose one more passes. If one of those passes are failed, okay. If one of them fails, I can choose one more pass. That's easy. And those passes are destroyed, are completely separated from each other. You know. So, for example, if I lost this switch in the left side in tier 2, okay, in the second tier, I lost the left switch in the second tier. Okay, simply I can use one more switch instead of that one to create a pass toward, for example, rack number 1. That is simple. So now one user can ask me a question. Okay, this question will be forwarded to the border router. It will forwarded to tier 1 and then tier 2, and finally it will forwarded to the desired rack. Okay, but how? During this pass, when I forward this request from the routers toward the first level switch, you can see here, firstly, the entered request is rerouted toward the load balancer. It's rerouted toward the load balancer. And then the load balancer decided that the server number X should answer this request, should answer this query. The load balancer defines which of those servers should answer this query. And according to this recommendation, my traffic is forwarded, for example, toward this rack. The load balancer defines that rack. The load balancer has enough information about the status of the network, about the current status of the network. So it decided, okay, for example, these servers are busy. Okay, this one is not busy. This is an empty server. So this request must be forwarded toward this server. You server, answer to this question. Okay. So the load balancer decided about the destination, about the server, which server should answer this. The load balancer defined this server. Maybe sometimes we have some internal traffics between different servers. For example, most of my servers are application servers, but sometimes I need some queries. I need to ask some queries from data center, for example, database servers. So I have some some internal traffics too. Okay, I have some external traffics plus some internal traffics in data centers. But those internal traffics can be handled internally. The load balancer just think about the external traffics. Mostly, it does not care about the internal traffics. So, when we are talking about data center networking, we need to define some special protocols for data centers. We need to propose some special networking capabilities in layer 2, in link layer. Okay, we need to define some special protocols for transport layer. For example, we need explicitly define the congestion if it arises in the network. We need some special version of TCP for data centers. We need special routings or special management in layer 3. Layer 2, layer 3, layer 4. We need special protocols. Special protocols for data centers because it's a special place with special requirements. So I need something special for this place. In data centers, we are using SDN widely. We are placing services between different racks, between different servers to minimize internal traffics between layer 1, layer 2, between the servers or something like that. It's need strong management techniques to manage all of these. Layer 2, special layer 2, special layer 3, special layer 4. Okay? This is the last slide that we talked about it in this course. No, Zahra, Donna said, no. This is the last slide. Just we talked about some special part of this chapter 6. Just we talked about switches, VLANs, MPLS, and data center networking. Nothing more. For the final exam, you need to read just these parts, not the whole chapter, okay? Just read these parts. Switches, VLANs, MPLS, and data centers. I said, Yusuf Muhammad, I said, just read. Yes, just read slides 16 to 92. Just this one. That's it. For the final exam, just, yes. Come on. Wait a minute, please. I will be back. Please. No, it's not. It's not too much. Don't worry, just read it. It will be finished. Don't worry, Hale Hassan. Okay, any question?